Okay, let's go ahead and get started with 20.2. This is going to be a little different than anything that that we have done so far in terms of balancing equations. Balancing an oxidation-reduction equation is a little more difficult than a normal equation. You have to take charge, transfer of electrons, all that stuff into account. So this is a good method for doing it. It's pretty straightforward once you learn the process. Like I said, it's going to look a little different, but then once you learn it, it's going to be the same pretty much every time, so it shouldn't be that big of a deal. You should look at the steps on page 847 in your book. This will basically tell you step by step how to do this. Okay, so we're going to use what's called the half-reaction method, and basically what we do, and it says here on paper only, notice, this is not what's really happening in the solution, but on paper we're going to kind of separate the oxidation and the reduction, balance them separately, and then kind of add them back together at the end. So this is just a kind of a trick that you can use to balance these things. So let's look at an example here. Well, okay, here's the rules, like they have them in the book, so you can look over those. It's not going to make a lot of sense until we actually start doing it. So we've got a reaction here. MnO4 minus, which is permanganate, and or manganate. Can't remember. I think that's permanganate. And the C2O42 minus, which is oxalate. So we're basically reacting those two with one another. And this is sometimes called the skeleton equation. So this is basically what's in the solution. The two things that we initially add, and so then we're trying to figure out when it actually reacts, what's going to happen. Now, one important thing to realize about these redox reactions is they usually take place either in an acidic solution or in a basic solution, one of the two. A lot of times they just won't happen unless they have H plus ions or OH minus ions that they can use to help them do the process. So you just got to keep that in mind, that we've got H plus ions running around if it says it's in acidic solution, or if it says it's in basic solution, we've got OH minus ions running around. Okay. So the first thing we're going to do is assign oxidation numbers. The manganese has a 7 plus. Each oxygen has a 2 minus, and there are 4 of them, so that's going to be an 8 minus. So in order to be an overall 1 minus, the manganese has to be a 7 plus. Hopefully you're okay now at assigning those oxidation numbers. Hopefully you got some practice on that during class today. And then you can figure out which ones are getting reduced and which ones are getting oxidized. The manganese is going from a 7 plus to a 2 plus, so it's getting reduced. Remember, Leo goes Gur. Lose electrons, oxidation, gain electrons, reduction. Okay, and so the manganese is gaining electrons because it's being reduced in charge, so it's being reduced. The carbon goes from 3 plus to a 4 plus, so that's the one that's being oxidized. Okay, so now that we know that, we can kind of write our half reactions here. So what you do is split these apart. Okay, and so we're starting with the oxidation half reaction here. So the C2O42 minus is going to CO2. Alright, so we're just basically taking this and this, separating it into a half reaction. And then we're going to balance the atoms first. So you always balance the atoms, make sure you have the right number of atoms on each side. Okay, so to do that, if we put a 2 in front of the CO2, that gives us 2 carbons, 4 oxygens on each side of the equation. Okay, now we have to balance charge, because right now we've got a 2 minus on this side and nothing on the other side, and that's not okay. Law of conservation of mass says that we need to conserve electrons as well as atoms. So what we have to do now is basically add 2 electrons to the right side. Okay, and so that will balance out our charge. So basically what that's showing is that the carbon here lost 2 electrons in this process. Lose electrons, oxidation. Okay? Alright, now we're going to do the reduction half reaction. That's the manganese MnO4 minus to Mn2 plus. And this is where it gets a little weird. Okay? Because right now we have oxygen on the left side of the equation, but not on the right side. So what we have to do is we have to basically think about some of the other things that we have in that solution. Okay? Right now, remember I said these take place in acidic solution. This one takes place in acidic solution. And I'm not sure that it even said that. Which is bad, but this one takes place in acidic solution. Okay? So the two things we have available to us that we can just use because they're going to be in the solution, water and H plus ions, okay? And we have both of those things just floating around in the solution so we can use them when we're balancing our equation. So H2O has oxygen in it, so the water molecules themselves might actually be involved in this reaction. So we're going to put 4 water molecules on the right side because there's 4 oxygens over here. Okay, so that's going to balance our oxygens. But now we just created hydrogens on the right side of the equation. There are 8 hydrogens on the right side, and there are none on the left. So what we have to do is add these 8 H pluses to the left side. Because remember, I said we can do that. We've got H plus in the solution. And that balances out all of our atoms. Okay? However, at that point, our charge is not balanced because we've got an 8 plus from the hydrogens here, and we've got a 1 minus from this MnO4 minus, so that's a total of 7 plus on that side. And there's only a 2 plus total charge on the right side. Okay, so we're off. So then what we do is we add 5 electrons to the left side. Whichever side has the greater charge, you'll add the electrons to that side. Okay? And we're going to add 5, so now we've got an overall charge of 2 plus on this side, because we just reduced that 7 plus down to a 2 plus, and then we've got a 2 plus on this side, so now our charge is balanced. Okay? So now we're going to look at both of those half reactions together. Now the rule here, and this is, I think, part... number 3 in your rules on page 847. Multiply the half reactions by integers if necessary so the number of electrons lost in one half reaction equals the number of electrons gained in the other. So basically what we're going to do here, we've got 2 electrons being lost in the first reaction, 5 electrons being gained in the second one. There's no number we can multiply the first equation by to make it be 5 electrons. Okay, so what we have to do is kind of like a least common multiple thing. Okay, so we're going to multiply this top equation by 5, multiply the bottom one by 2. When we do that, we'll have 10 electrons being lost in the first one, 10 electrons being gained in the second one, because you have to, those electrons have to go somewhere. So the number of electrons being lost in the first one has to equal the number of electrons being gained in the second reaction. Okay? So once we do that, we end up with these coefficients here, 5, 10, and 10, 10, 16, 2, 2, 8. And that's just because of what we multiplied each of those by. Now notice, again, we're losing 10 electrons in the oxidation, we're gaining 10 in the reduction. So that's right. Okay, that's correct, because the number of electrons being lost has to equal the number of electrons being gained. Now you can just add these together, do kind of a Hess's law type thing. Okay? And so there's your overall reaction down here. Now notice we've got 10 electrons on the left side, 10 electrons on the right side. And it's typical when you have something on both sides of the reaction to just kind of cross it out, cancel it out. Okay? So the electrons go away, and what we end up with is this overall equation down here. Okay? And so that is your balanced redox reaction for the reaction of the permanganate and the oxalate ions. So, kind of complicated, but that's how it works, and it's a little different than normal balancing, but again, it's just a process, and it's the same every time. Okay, so let's practice this. So we've got this equation here, Cr2O72 minus and Cl minus, and Cr3 plus and Cl2. It doesn't really matter all that much that you identify which one is being oxidized, which one's being reduced here. You'll figure it out once you start the half reactions. But what you have to identify is what your two half reactions are. Okay, one of my half reactions here is going to be the Cr2O72 minus going to Cr3 plus, and the reason I know that is because they both have chromium in them. Okay, and then my other half reaction is the Cl minus going to Cl2, and again I know that because they both have chlorine in it. Okay. So usually it's going to be fairly obvious what your two half reactions need to be. So I'm just going to start with the Cr2O72 minus going to Cr3 plus. Okay, so first thing we need to do is balance our chromiums. Okay, and that's important. It's an easy step to forget, but there's 2 on the left side, so we need to put a 2 here to balance that. The next thing we need to do is balance our oxygens. Okay, now again, there are no oxygens on the right side, so what we have to do is bring water into this reaction. Okay, there are 7 oxygens on the left side, so I'm going to put 7 water molecules on the right. That'll balance my oxygens, but now I have hydrogens that kind of came out of nowhere, 14 of them, so now I need to put 14 H pluses on the left side. Okay, then I need to think about overall charge, and then we'll figure out our electrons here. So see, I didn't leave myself enough room. We've got a 14 plus coming from the hydrogens, and a 2 minus coming from the dichromate. So that's a 12 plus overall on this side of the equation. And then we've got 2 Cr3 pluses on the right side, so that's a 6 plus overall. So we need 6 electrons on the left side to balance that out. So again, I didn't leave myself enough room here, so I'm just going to put that down below. Sorry, that's sloppy. So there's one of my half reactions right there. Okay, my other half reaction is going to be the Cl minus going to Cl2. And that one's a little bit easier to balance because there's no oxygen in here, so that we don't have to add H2O or anything like that. So I'm going to put a 2 in front of this Cl minus because that balances out my chlorines. But now I've got a total of a 2 minus charge on this side and a 0 on this side. So I'm going to have to put 2 electrons over here to balance out the charge. Okay. Now, if you do both half reactions and you end up with the electrons on the same side of both, that's probably a clue you did something wrong. Okay, you should end up with the electrons on opposite sides. So our first half reaction, the electrons are on the reactant side. Our second one, they're on the product side, so that's good. Okay, so then you need to multiply the equations by whatever you need to make sure that you've got the same number of electrons on both sides, which here I just need to multiply the bottom reaction by 3. That'll give me 6 electrons on the product side, and then that's even. Okay, so then we're going to add all this up, and I'm going to run out of room here, but we've got 6 electrons plus 14H plus Cr2O72 minus plus 6 Cl minus. Okay, so that's everything on the reactant side, and that yields 2 Cr3 plus plus 7H2O plus 3 Cl2 plus 6 electrons. Okay, so that's our reaction. And again, the only thing that cancels out here is the 6 electrons on both sides. So there's your overall balanced equation for that skeleton reaction. Okay, one more thing we need to talk about. In basic solution, sometimes the reaction can occur in a basic solution as opposed to an acidic. Well, the trick here is that we're going to pretend we're an acidic solution on paper, and then we're going to kind of go back and fix it at the end. Okay, it's just a little bit easier to do it this way, so I'm just going to have to show you an example of this. Okay, so here's your reaction. So this is in a basic solution. Okay, now the problem with it being in a basic solution is if I'm trying to figure out where I can write this. If I balance this as we're in a basic solution, so let's say I've got the MnO4 minus going to MnO2. So there's one of my half reactions here. Okay, so I'm going to have to add H2O to this side, 2 of them, to balance out my oxygens. But then instead of using H+, I would use OH-, okay, to balance my hydrogen. So I've got 4 hydrogens, so I'd have to add 4 OH- to this side. Well, maybe you can already see how this gets complicated because I just added more oxygens to the left side. So then now I'm going back and forth trying to balance my oxygens and my hydrogens, and it just gets really messy. Okay, so it's easier if we pretend we're in an acidic solution, so we add H+ instead of OH-. And then, like I said, we'll go back and I'll show you how to fix that at the end. Okay, so hopefully you can identify our 2 half reactions here. Those are the ones that contain the CN, and then you've got the MnO4 minus and the MnO2. Oh, by the way, I should go back, show you on this other one. You can figure out which one is the oxidation, which one is the reduction after you have done the half reactions, because this one at the top, the 6 electrons on the reactant side, that means that it's gaining 6 electrons. So the Cr2O72 minus is the one that's gaining electrons, so that's the one that's being reduced. So that's the reduction part of the reaction. The one that's losing electrons is the one that has the electrons on the product side, so that's the Cl minus, that's the one that's being oxidized, LEO, lose electrons oxidation. Okay, so you can kind of look at it at the end and figure it out. You don't have to worry about it at the beginning. Okay, so we've got Cn minus, going to CnO minus. Okay, so the carbon and the nitrogen are balanced already. We need to balance the oxygen by adding just 1 H2O to this side. And then we need to balance our hydrogen by adding 2 H+ to this side. Okay, so now that's balanced. Now we got to look at our charge. Okay, overall this is a 1- on this side. This is a 1+ on this side. So in order to get that balanced, we have to add 2 electrons to this side. Okay, so now that becomes a 1- just like on the other side. So that's balanced. The second, and again, I'm adding H+. That's not really what's happening in solution. It's OH-, not H+, but we're pretending for a second here. The second half reaction, MnO4- yields MnO2. Okay, in that one, the manganese is already balanced, but to balance the oxygens, I need to add 2 H2Os to this side. We already talked about that. That gives me 4 extra H's, so I'm going to add 4 H+ to this side. Okay, so now my overall charge on this side is a 3+, because I've got the 4 H+ and then the minus from the manganate. And then on the other side, I have a 0 charge. It's neutral. So I'm going to need to add 3 electrons to this side to balance out my charges. Okay, then on this one, I have to multiply both of them to get them to the least common multiple. So I'm going to have to multiply this top one by 3, and I'm going to have to multiply the bottom one by 2. And that will give me the right number here. Okay, now, we have to add all this together, so we've got 3H2O plus 3Cn minus plus 6 electrons plus 8 H pluses plus 2 MnO4 minus. Yields, that's everything on the reactant side, not the product side. 3 CnO minus plus 6 H plus 6 electrons plus 2 MnO2 plus 4 H2O. Okay, now you're going to notice several things here. Okay, first of all, there's some stuff we can cancel out. Okay, the electrons completely go away. The H pluses, we have some on both sides. Okay, so these go away, and now this coefficient gets changed to a 2. And then this water goes away because there's water on both sides, and there's no coefficient in front of the H2O. Okay, so now that would be balanced. We would be done if this was an acidic solution. The problem is we did this in a basic solution, and there should not be any H plus in a basic solution. Okay, so what I'm going to do here is I'm going to kind of do a little algebra trick. And you know, in a typical algebra problem, if you add the same thing to both sides, then it doesn't change the value of the equality. Okay, we're basically going to do the same thing here. We're going to add OH minus to both sides of the equation. Okay, so I'm going to add OH minus, I'm sorry, this is getting really sloppy, OH minus to the reactant side, and I'm going to add OH minus to the product side. Now I'm going to add 2 OH minuses on each side. And the reason for that is because I want to basically neutralize that H plus. Okay? So, watch what this does. If I add the 2 OH minuses, it's going to react with the 2 H pluses and make 2 water molecules. Okay? And so then what I end up with here is 2 H2O. instead of 2 H pluses, okay? And then everything else is basically the same on the reactant side. 3Cn minus plus 2 MnO4 minus yields 3 CnO minus plus 2 MnO2 plus H2O plus 2 OH minus. Okay, there's no H pluses on the product side to neutralize the OH minus, so the OH minus is still there. Okay, but again, on the reactant side, the OH minus reacted with the H plus, and it made 2 water molecules. Okay, now again, this is all just completely hypothetical. This is not the way it's really happening, but it will get us to the right answer. All right. So then you have to do one more cancellation here, because now we've got water on both sides again. This goes away, and the coefficient on the H2O goes away. And so then we end up with our overall balanced equation, H2O plus 3Cn minus plus 2 MnO4 minus yields 3CnO minus plus 2 MnO2 plus 2 OH minus. Okay? And you can check both charge and the number of atoms here. That's always kind of a good thing to do at the end, just to make sure you're on the right track. And you can see if you're you got it correct. You would have to check again both the number of atoms and the charge on both sides. Okay, just a quick check of the charge. It looks like we've got a 3 minus 5 minus on the left side, and then we've got a 3 minus 5 minus on the right side. So the charge looks good, so that's promising. Then we just have to count the number of each of the different types of atoms. We've got 2 hydrogens on the left. We've got 2 hydrogens on the right. We've got 9 oxygens on the left. We've got 3, 7, 8, 9 oxygens on the right, so that's good. 3 carbons, 3 carbons, 3 nitrogens, 3 nitrogens. 2 manganese, 2 manganese, 2 manganese. Okay, so everything's balanced, and that's the way that you balance redox reactions. A little bit tricky, but it's, like I said, it's the same process every time, so once you learn it, it's not that bad. Okay, we'll see you in class.